only a variation in the temperature with respect to time. So that when we have two of these variables, one is position and one is time, in the lump parameter model, the position was not important. What was important was the time. And we had seen that the relationship that we had developed was this, that T minus T infinity divided by Ti minus T infinity was equal to e to the power minus HA rho VCP, all these physical properties, into T. So that there was a relationship between time and temperature. Position was not important out here. And this, in order for this model to be successful, we had said that what we had to do is that we had to calculate the Biot number and find out whether this Biot number was less than 0.1. If it was, then yes, what we are talking about is fine. And if not, we cannot use this model for our calculations. Now, today, let us look at a few situations when we cannot use these situations, when we cannot use the lump parameter model, and where the internal resistance is not small, then what do we do? The internal resistance is not small, which essentially means that we cannot use the lump parameter model, and the temperature inside the solid is not constant. There is a variation with respect to distance, or there's a spatial variation also. So the first case that we consider is one in which the surface convective resistance is negligible and compared to the internal resistance. That means when we talk about, that means it's a situation where there is a large heat transfer coefficient. That means H value is large and the conductive resistance is also large. That means H being large essentially means that the surface convective resistance is negligible or the coefficient is large. H being the coefficient is large and the resistance is negligible. That means convective resistance is not there out here, but there is a conductive resistance inside the solid because of which there is a variation in temperature. Now, unsteady state, we consider unsteady state convection in the x direction. This is my x direction as denoted by this arrow. And this is a flat plate which has got a thickness of 2h. This is the thickness of this plate. At time t equal to 0, the temperature of this plate is constant throughout. Everywhere it is constant, this straight dotted line which is there. And this value is equal to T0. That is at time t equal to 0. At time t equal to t, when there is a variation in temperature as the time changes, the values of temperature on either side of this flat plate is T1 and T2. T1 on the left-hand side and T1 also on the right-hand side. Because of the fact that there is very low surface convective resistance, that means conduction is very high. That means what we have is the constant temperatures out here. And there's a variation in temperature inside the solid, which we can see out here. And so we can have to find out what is the variation of this temperature with respect to distance and with respect to time. So since we are looking at the rate of heat transfer only in one direction, that is the x direction, we can say that we had developed this expression in the last class. I'll just go back and show you where we had developed this expression. Okay. This is where we had developed this expression, that if there was unsteady state heat transfer in only one direction, we can write this as del T, that means change in temperature due to change in time, is equal to alpha thermal diffusivity into del 2T by del X2. So here we have X, we have time, and we have temperature all being related. Now, if there are three directions, this is what we would have been. But in this case, we have only one direction that we are talking about. Okay, so now look at the boundary conditions of this. At time t equal to 0, temperature is equal to T naught or T0 at all possible x values, which is given by this particular straight line. At all x values, at time t equal to 0, temperature is equal to T0. And at time t equal to t, there are two possible conditions. At x equal to 0, that means on the left-hand side, and at x equal to 2h, which is on the right-hand side. Under both these cases, T is equal to T1 and T is again equal to T1. So these are the two of these temperatures that are there on either side. Now, instead of using del 2, what did we have? We had out here, let me just write it again. We had del T, del TA. change in time is equal to alpha delta t del x2. Now the thing is that the temperature is a value which can go from any value, starting from any value, can end up in any particular value. So in order to understand this better, what we do is that we write a dimensionless temperature. And because we write a dimensionless temperature, the range of this temperature varies between 0 and 1. So how do we write this dimensionless temperature? This is written as y. Y is equal to T1 minus T divided by T1 minus T naught. So this is how we define the dimensionless temperature. So if I write this, differentiate this with respect to time, what happens is this just comes out. These are all constant terms. T1 and T naught are all constant terms. So dy dt is equal to alpha differentiated twice del to y by del x2. So we just replacing the the temperature term by a dimensionless temperature term. With the range of this dimensionless temperature goes from 0 to 1. So which we can see out here, that when we redefine the boundary conditions for the first case, when time t equal to 0 at all possible x's, your time, this temperature becomes equal to temperature T naught. We have replaced T by T naught. So the numerator and the denominator is the same. So this becomes equal to 1. Now at time t equal to t at x equal to 0 and at time t equal to t at x equal to 2h, the temperature now becomes equal to T1. At both the ends, the temperature is equal to T1. So numerator is T1 minus T1, which essentially becomes equal to 0, and this one also becomes equal to 0. If I solve this equation, what we come up with is a solution which is y is equal to e to the power minus a square into alpha t. In brackets is a cos ax plus b sine ax. A and b, this a and this b are constants, and a is a parameter. So this is how this is the solution to the problem. Now, if I put the initial and the boundary conditions in this solution and replace the y value by the dimensionless temperature, what we come up with is an infinite Fourier series. So T1 minus T divided by T1 minus T naught is equal to 4 by pi. And in brackets, in the first case, it is 1 by 1 exponential minus 1 square pi square alpha t by 4h square sine 1 pi ax by 2h plus this 1 gets replaced by a 3, notice. So this becomes 1/3 exponential. Instead of 1 square, we now have 3 square pi square alpha t by 4h square sine. Again, this 1 gets replaced by 3 pi x by 2h. Third term, the 3 gets replaced by a 5, that means 1/5 exponential minus 5 square pi square alpha t by 4h square sine 5 pi x by 2h plus so on and so forth. The 5 will then become a 7 and go on and so on and so forth. Since this is an infinite series, if I want to actually find out the temperature at a particular case, I can say consider the first term and the second term and put a bracket out here. So if I want to actually calculate the value, what is the information that I need? I need the value of alpha, which essentially means I need my thermal diffusivity, which are physical properties, K by rho Cp. T is the time after which this value is coming out. 2H is the thickness of my plate as shown out here. And X is what distance I want to find out the temperature. At what distance do I want to find it out, at x equal to 0 or x equal to h or x equal to 2h, whatever is the case, the x value will be denoted by that. I can do that, and this expression will give me the temperature at any position x at any time t. These equations, of course, are quite time consuming, and we have charts which are available for us to use and do the calculation. But if you still want to use these, you can just truncate it or cut it off after this, because it's an infinite series, there is no end to it. But the terms become smaller as we go on increasing the value. So we can say maybe take 2 terms or 3 terms and calculate the temperature based on it. Next comes the unsteady state heat conduction in a semi-infinite solid. So what do you mean by semi-infinite solid? If you look at this picture, you will see that what we have is that there is a perfect end to this side, and here I put it as a end which does not we do not know where it ends. So it is infinitely long in this direction or the x direction. And there is a proper end on this side and this side. This side is fixed, but in the x direction, the length of the solid is infinite. So this is called a semi-infinite solid, which is there. A semi-infinite solid extends to infinity in the x direction, and heat conduction occurs only in the x direction. We are not going to consider heat conduction either in the y or the z direction, that is there. Only in the x direction, which is the infinite distance. At time t equal to 0, the solid is suddenly exposed to or immersed in a large mass of ambient fluid at a temperature of T1. So what do I say? I said that this body is now placed in a situation where the ambient temperature is equal to T1. In the previous case, we had assumed that this resistance, that is the resistance due to convective heat transfer, was negligible, very small. Whatever resistance was there was inside the solid. But here that is not the case. This is H becomes important. So there is a dip out here. That means there is convective heat transfer out here. And inside the solid also there is a change in temperature. So at time t equal to 0, the temperature would have been constant at T0. Now when this solid is exposed to an external conditions where the ambient temperature is T1, then the temperature goes from here, there's a dip in the temperature. At the end, the temperature is Tt. And as time changes, there is a change in the temperature inside the solid. Now, I'm not going to the mathematical derivation of how we come to the final solution, but the solution to this differential equation under these conditions, if you have these kind of conditions, is T minus T0, D1 minus T0. If you remember, how did we define y? Y was different. Y was T1 minus T and T1 minus T0. But here I'm writing T minus T0 and T1 minus T0. So essentially what I'm writing is this is 1 minus y. This is equal to ERFC. ERFC is called the complementary error function. What is error function now? First, let me talk about error function, then I'll tell you what is complementary error function. So if you want to understand what is error function is a standard mathematical function. And if you still want to know what is that, it is an error function of z, for example, is equal to 2 by square root of pi, integrating it from 0 to z, e to the power minus t squared dt. So if you plot the error function versus this value, you will get a plot like this. So these are like standard mathematical functions, just like you have the sine function or the cos function or the tangent function. And the values of the error functions, they range from 0 to 1. So in the next question, you would say, where do I get these error functions? These are available in textbooks. I will show you right now where do we find the value of error functions. And 1 minus the error function is called the complementary error function. EFRC, that is the complementary error function, is equal to 1 minus error function. Remember, the value of error function goes from 0 to 1. So I will show you in the next slide some values of these error functions. So these are the values of error function. So if you want to calculate the value of error function z, if you know the value, first you calculate the values of z, then the error function of z is, you can go to the tables or which are available and find out what is the error function. And I told you that if this is my error function, your complementary error function is 1 minus the error function. So if this is 0, complementary error function is 1. So on and so forth, we can go from here to here and find out what is the complementary error function. Okay, so what do I do from here? Now let's see what is out here. So this is 1 minus y is equal to a complementary error function of x divided by 2 square root of alpha into t. X is the distance at which, this is the distance at which you want to find out what is the temperature. And t is the time after which you want to find out. Alpha is my thermal diffusivity. So this will give me a numerical value. So once I have the numerical value, I can go to this chart. That means I have the numerical value of, say, eta. And then I can find out what is the error function of that particular eta from this particular table. Okay, so error function, this is what we have. Next is minus exponential h square root of alpha into t. Alpha is my thermal diffusivity, t is my time, h is my heat transfer, convective heat transfer coefficient. This is the conductive thermal conductivity of the solid material, which is out here. This into multiplied by x by square root of alpha t plus h square root of alpha t by k. So all of these terms are known to me. This is multiplied by the error function of x by 2 square root of alpha t plus h plus square root of alpha t by k. So again, this is another term which we can numerically calculate and find out what is the error function of that particular one. So this is something that we have to do the calculation. Obviously, so what are the things that first you need to know the value of h, you need to know the value of k, you need to know the value of alpha, t, and x. Once you know all of that, you can calculate this term, you can calculate this term, you can calculate this term. From the error function tables, you can find out the values of complementary error function, this one. You can find out the value of the complementary error function, this one. This complementary error function multiplied by this term, and it will become a single term, and you have to find out the exponential of that. So obviously, this is a long or a little more complicated mathematical expressions that we have to slowly calculate. So instead of that, what the people have done is that they have plotted this in the form of figures. So when you have this plot in the form of figures, what do I have out here? Look at the x-axis. X-axis is x by 2 square root of alpha into t. This is my term in the x-axis, which essentially means this is my term, which is out here. This is my term, which is there in the x-axis. X by 2 square root of alpha t. So what is the other term that we are talking about? The other term is h square root of alpha t by k. So these different lines which are drawn out here, these blue lines, these are for different values of h square root of alpha t by k. So this one and this one, we can find out the numerical values. And from this numerical, say for example, if this value x by 2 square root of alpha t is equal to 1, then I go along this particular line. And if my value of h square root of alpha t by k is also equal to 1, just for the sake of estimations I'm saying, then we go up and reach the line where this is 1, go to the left hand side and find out what is this. This becomes equal to 0.06. So if my t minus t naught divided by t1 minus t naught is equal to 0.06, knowing the values of t1 and t naught, I can calculate the value of t. So this is how, instead of using the whole equation, there are figures like this available, which we can use to calculate the value of the temperature at any position and at any particular time for a semi-infinite solid. So in order to understand that what is a semi-infinite solid, let us do a problem which will help us understand a practical situation. Let me read out the problem, then I will explain it to you. The depth in the soil of the earth at which freezing temperatures penetrate is often of importance in agriculture and construction. During a certain day in the fall season, the temperature in the earth is constant at 15.6 degrees centigrade to a depth of several meters. So what does this mean? This means that when we have, say, for example, the ground soil, this kind of condition is very prevalent in very cold countries. Fortunately, we don't have too many places in India where the ground freezes up during winter. That means barf गिर जाता है इसके ऊपर. ऐसा situation नहीं होता है. Suppose this is my soil. इसके ऊपर पेड़ पौधे जो भी है, whatever is there is out here. So this is my soil. Now this soil can extend in this direction up to an infinite length. So this soil is considered to be an semi-infinite solid. Now what happens is the ground, zameen jo hai, that is considered to be a semi-infinite solid because it extends to infinity in the x direction. And this is my direction of x I am talking about. Now the thing is that agar iske upar, now we want to know ki, you know that most plants will not survive when the temperatures become very, very low. That means at sub-zero temperatures. So we want to find out ki in case there is snowfall. When there is snowfall, the temperatures on the surface will be equal to 0 or maybe even less than 0. So when we have a situation like this, what is the temperature inside the ground? If there are any living creatures inside, if there are any seeds, etc., will they be able to survive or not? That is what we are trying to understand from this. This is a situation we don't see much in our country, but in cold countries or in the regions of our country like Kashmir, etc., where there is it's very cold and we have a snowfall for a large part of the year. These kind of problems, practical problems leading to this kind of unsteady state heat transfer is actually a practical problem. So what did they say? During a certain day in the fall season essentially means autumn. Autumn essentially is about a temperature in September, October, that is kind of the autumn season. The temperature in the earth is constant at 15.6 degrees centigrade to a depth of several meters. So kahin pe bhi hum log dekh le, the temperature is 15.6 degrees centigrade inside the soil. Then what do they say? A cold wave suddenly reduces the air temperature from 15.6 to minus 17.8. So initially the temperature everywhere above, below everything was 15.6 degrees centigrade. Then you suddenly have a cold wind and this temperature on the surface becomes essentially equal to 17.8 degrees centigrade. There is a cold wind blowing which is at this particular temperature. So the air temperature goes down from 15.6 to minus 17.8 degrees centigrade. Now you're told the convective coefficient above the soil, that means the convective heat transfer, essentially you're given the value of say H out here, is 11.36 watt per meter square Kelvin. The soil properties, ये soil के जो properties है, that means the thermal diffusivity alpha is equal to 4.65 into 10 to the power minus 7 meters square per second. And the thermal conductivity of the soil is given as 0.865 watt per meter Kelvin. What you're asked to find out is what is the surface temperature after 5 hours. So once again, let me tell you what is the situation. We have the soil on the ground pe, the temperature is 15.6 degrees centigrade. So soil ke upar bhi utna hi temperature hai, soil ke andar bhi utna hi hai. After some time, it so happens that the temperature of the atmosphere suddenly falls. That means there's a decrease in temperature, most probably due to snowfall. And this temperature now becomes minus 17.8 degrees centigrade. Agar bahar ka air ka temperature minus 17.8 degrees centigrade hai, so obviously the soil and inside the temperature is also going to change. The question that you've been asked to is, what is the surface temperature after 5 hours? 5 घंटे बाद surface का temperature कितना है, यहाँ का temperature कितना है, and to what depth in the soil will the freezing temperature of 0 degrees centigrade penetrate in 5 hours? So the second question is, after 5 hours, at what distance will the temperature be equal to 0 degrees centigrade? So beyond that, the temperature is going to be higher than 0 degree, but till what depth will the temperature change from minus 17.8 to say 0 degrees centigrade? So now we can see, say this is my infinite, I'm showing the direction in this case as the depth of the soil. This is the surface of my soil. And this is the temperature that has come down to minus 17.8 degrees centigrade. And let us see how the temperature changes. So for this, what we will do is we will try to use the graph for our calculation. So in the case of the graph, which we have seen out here, we have to calculate x by 2 square root of alpha t. Now, what is x? X is the distance at which we want to calculate the value. The first thing we want to find out is the surface temperature. Let me just get a different colored pen out here. Okay. So the first thing we need to know is the surface temperature. When we are talking about the surface temperature, that means the temperature out here. Here the value of x is equal to 0. So we have the first value is when x is equal to 0. So x divided by 2 square root of, we can write out the value of alpha, and temperature is after 5 hours. And because we're doing it in terms of watts, we will multiply this in terms, turn it into seconds. This value comes out to be equal to 0 because my numerator is 0. The other term that we need to find out is h by square root of alpha t by k. We know the value of h given to me. We know the value of alpha. Time is 5 hours converted to seconds. K value we know. And in that case, h by square root of alpha t by k becomes equal to 1.2. So now we have to calculate what is the temperature when we have the x value equal to the x-axis, which is equal to 0, and the different lines which are equal to 1.2. So let us go back here and see. So x is equal to 0. So we are going from this point to a value where your h by square root of alpha t is equal to 1.2. So this is the value of 1 and this is the value of 1.2. So we increase it slightly from here, and what we come up with is that the value of t minus t naught, t1 minus t naught is equal to 0.63. Now what is t naught? T naught is the initial temperature. Initial temperature was 15.6. Convert it into Kelvin so that we have all positive numbers, no negative numbers we have to deal with. And T1 is the temperature which has now gone down to minus 17.8. Again, converted into Kelvin. So we have 255.2. Put it in this expression. So T is equal to T naught, which is 288.6, that is T naught, plus 0.63 multiplied by T1 minus T naught. T1 is equal to 255.2 and T naught is equal to 288.6. So this term essentially becomes a negative term. So the temperature comes out to be 267.76 Kelvin or minus 5.44 degrees centigrade. So even though the air outside is at a temperature of minus 17.8, the surface temperature only comes down to minus 5.44 after a period of 5 hours. Only 5.44 after a period of 5 hours. So 17.8 said this becomes 5.44. Now with the next thing we have to do is find at what distance is the value equal to 0 degrees centigrade. So for this part 2, when the temperature has to be 0 degrees centigrade. So now in this case, we know the temperature, we want to find out the distance. So temperature is 0 degree, that means 273. And this is T naught is minus 288.6. T1 is 255.2 minus 288.6. So this comes out to be 0.469. So we have to find out where is this value of 0.469 in this particular case. So suppose we have found that out. And then we also know that h by square root of alpha t by k, which again we have to calculate it after 5 hours, so the time remains the same, is equal to 1.2. So we go from this one line and find out what the imaginary line of 1.2, which I'm drawing out here, this one out here, and this is equal to, this is 1.2, and here we have 0.467. The intersection of that, if we drop it at the bottom, then this term, that is x by 2 square root of alpha t, comes out to be 0.16. So this is the value of x by 2 square root of alpha t. Now we need to know the value of x because we know all the other terms. So 0.16 is multiplied by 2 times square root of, put in the value of alpha, and the time is again equal to 5 hours written in terms of seconds. So this comes out to be equal to 0.0293 meters. It is up to a depth of this that we have the temperature going to 0 degrees centigrade. Beyond that, the temperature will be above 0 degree and will have some positive value in terms of centigrade also. So this is how we can use this figure for a semi-infinite solid. So for your problems, what would be important is to identify which kind of problem that we are dealing with. The next kind of geometry that we will talk about and end our lecture on this unsteady state heat transfer is when we are talking about unsteady state heat conduction in a large flat plate. So what is a large flat plate? A large flat plate is defined as something. Here there are finite ends out here, okay? Finite ends out here, and in this direction we have an infinite growth. In this direction also we have an infinite growth. That means in the z direction and the y direction there is infinite growth, either this side or this side. But there is not in the x direction, which is out here, things are finite. So this is a large flat plate which will have a thickness, and then it is and the extensions will be infinite in the other directions. So so what is a large flat plate? Let us see. It has a thickness of 2x1. So the entire thickness of this plate is equal to 2 times x1, where the center, like x1, one extends from the center in this particular direction, and the other one extends in the opposite direction. But together, the thickness becomes 2 times x1. So this is, and where is the direction of x? From the center of this, the direction of x is going from the center upwards. So that is my direction of x that we have. So the plate considered here has a thickness of 2x1 in the x direction and large or infinite dimensions in the y and z direction. Now heat is conducted only from the two flat and parallel surfaces in the x direction. That means this side and particularly this side. The initial temperature at T equal to 0 is T0. Now, then we expose the solid to an environment at a temperature T1. So this case also, the H value, that is the heat transfer coefficient, the convective heat transfer coefficient is also important. And you're exposing the solid to a temperature of T1. And unsteady state heat conduction occurs. Surface resistance is present. That means that the resistance is substantial, so there is a resistance to convection. Now, the numerical solutions to these problems, or this kind of a geometry, as you can say, this is plotted graphically. Now, we try to find out in terms of graphs. So, what kind of graphs? That I will show you slowly. So, using the graphs of charts, which will be showing, we will be showing in the next slides. The temperature at any position in the plate and at any time T can be calculated. So you can calculate the temperature at any X value and at any T value. So let us see what kind of charts we have. So the dimensionless parameters which are used for these graphs and subsequent unsteady state charts, these are the parameters that we are talking about. One is called M. What is M? M is equal to K by Hx1. So this is 1 by the Biot number. So K is the thermal conductivity, H is the convective heat transfer coefficient, X is half my thickness. The next term is N. N is given as the sort of the dimensionless distance, which is X by X1. So what we are talking about, if this is X1, any X out here divided by the total distance x1. So x can, the ratio can go from 0 to 1. So n value can go from 0 to 1. The other term that is involved, which we're calling as capital X, is alpha t by x1 square. This is called the Fourier number. I'll tell you a little bit more about the Fourier number right now. So x1 alpha t by x1 into square, x1 square. So x is the distance from the center of the flat plate or cylinder or sphere. This picture I have shown you is for the flat plate. A similar condition can arise for a sphere or a cylinder where x is from the center outwards. X1 is 1/2 of the thickness of a flat plate or the radius of the cylinder or the radius of the sphere, whichever one the shape might be. Now, this Fourier number, since it's a number, it will always have a physical significance. The Fourier number is a measure of the heat conducted through the body relative to the heat stored. Let me show you this picture. So if there is heat going in, how much of heat is going out from the body and how much of heat is being stored in the body. So Fourier number is a ratio of heat conducted by the heat stored. So if I look at this, this is alpha t by, what did we have? x1 square. That means length square. So if I write this as length square, this is now alpha, you know, is k by rho Cp. This is the definition of alpha. We can take this t to the denominator out here. This t is taken to the denominator. We are multiplying the numerator and denominator both by L square. So there's an L square term out here. One of the L's is taken up, 1 by L likhne ke liye, into delta t. So we have written it in such that we have arranged it in such a manner that the numerator talks about the heat conducted across length L of a body, which has got a volume equal to L cube. And the denominator is the rate at which heat is stored in a body which has got a volume of L cube. So essentially, it is the Fourier number is a ratio of the heat conducted through the body to the heat which is stored in the body. Now, how do I do the calculations or find out the temperatures? Now, here is what we have is X value, that means the Fourier number. Fourier number calculate करने के लिए what do we need? We need alpha, thermal diffusivity. We need the time after which we are doing the calculation, and x1 squared. That means half thickness of the plate or the radius of a sphere or the radius of the cylinder is what we need. So once we have that value, next we also need to know the value of M and N. So you will see that each bunch of these lines, for example, this is for a value of M equal to 0. This bunch of lines is for a value equal to of either M equal to 0.5. This bunch is for M equal to 1, and this bunch is for M equal to 2. And the rest are again increasing out here. And for each of these M values, there are several N values. For example, in this set where M is equal to 1, N value ranges from 1, 0.8, 0.6, 0.4, 0.2, and 0. So all of these we try to write it so that there's a range of N values, and we can choose whichever values we need to do for our calculations. This figure I have taken from Genkoplis. Even if it's not very clear, you have the book with you. You can have a look at the book. Now, the question is, what did we say? We needed to find out the temperature at after a certain period of time, that at a different values of T and at different X values. So one important factor is when N is equal to 0. When is N equal to 0 out here? N equal to 0 means X is equal to 0. X equal to 0 is only possible when we are talking about the center temperature. So that becomes an important calculation when we are talking about our the calculations for our for any body that is there. We want to find out what is the temperature at the center of the body. So in that case, we have a situation where N is equal to 0. So for this, we can use N is equal to 0. We can use any of these charts to do the calculation also, but a more accurate chart for determining only the center temperature is given by Hessler. Remember this name. Hessler charts essentially help us our transient temperature nomographs. Transient temperature means unsteady state temperature. Nomographs means these are graphs where you can use it to calculate different values. So these are Hessler charts, gives us a very accurate way of calculating the center temperature. Not that we cannot calculate it from other figures also. Apart from the center temperature graphs, Hessler also prepared multiple charts for determining the temperatures at other positions. So when we talk about these Hessler charts, let's see what kind of charts we have. So for each geometry, what kind of geometries will we talk about? One is a flat plate, second is a cylinder, and third one is a sphere. So for each of these geometries, so the first figure will help us determine the temperature at the center of the geometry at a given time. So the Hessler chart will help us to calculate the center temperature. The second chart is to determine the temperature at other locations at the same time in terms of the initial temperature. The third one is that in order to determine the total amount of heat transfer up till this particular time t. So we will try to see these plots for the three different geometries. One is a flat plate, the second one is a cylinder, and third one is a sphere. So let us look at the first one. The first one is a Hessler chart for a plane wall of thickness equal to 2x1. Just like we had done. This is my, sorry. Just give me a moment. Let me erase this. Okay, so what we have right now is this particular figure that we have the thickness is 2x1. X is going from the center outwards, and at the surface this or this way, or this is coming down this way, depending on which direction you're going. So the center value is equal to x, and the center x value is equal to 0, and we are trying to find out what is the temperature at the center. So for that, if we are going to use this plot for a wall thickness of equal to 2x1, knowing the environmental temperature which is equal to T1 and the convection coefficient of H, the first thing we need to calculate is the Fourier number, which is alpha, that means thermal diffusivity, into the time after which we want to do this calculation, into the square of half the thickness. So once we have found the Fourier number, from this Fourier number, we take a value and go straight up. And up to which blue line? The blue lines represent 1 by Biot number. That means K by HL. So we know thermal conductivity, we know heat transfer coefficient, we know the distance at which we want to do the calculation. So once we have done that, then we can go see where they meet, and they go to the left hand side to calculate the temperature. This temperature is used for determining this graph is used for determining the temperature at the center of a large plate for unsteady state heat transfer. I told you there are 3 charts. Like I told you here, there are 3 charts. The first one is where we find out the temperature at the center of the body. The second chart, this is again for a flat plate, is in the x-axis. What do I have is 1 by a Biot number. That means K by Hx1. And these lines which are drawn are for x by x1 values, which is essentially equal to my n value that we had talked about. N value, this is equal to x by x1. So this range can go from 0 to 1. 0 would mean the center, 1 would mean the surface. So that's where we can go to these different lines. And knowing this 1 by Biot number, finding out at what point you want to find out the temperature, go to the left hand side, you will be able to calculate your temperature. And the last one, which corresponds again to a flat plate, is the value of where we are trying to find out the Q values, Q by Q max, and x-axis is equal to h squared alpha t by k squared. This is essentially equal to Biot number square into Fourier number. This and this different lines are drawn for different Biot numbers. From here we calculate, go there, and find out what is the amount of heat that has been generated. So these 3 figures that I have shown you are essentially for a flat plate. Similar figures are obtained for cylinders. I've written out here for a long cylinder, which is of radius r0, initially at a temperature of T0, then it has been exposed to an outside temperature of T1. Heat transfer coefficient is H. So these graphs look slightly different from each other, but if you look at the graph, you will see that in the corner of these graphs, we have written that this is for a plate, this is for a cylinder. So you cannot use these graphs interchangeably. You have to find out the right graph for your geometry. Again, calculate the Fourier number, calculate the Biot number. So 1 by Biot number, and this is Fourier number, and you can calculate the temperatures at the center of your cylinder. You can also calculate the temperature at any other position in the cylinder, and you can also find out what is the rate of heat transfer from any of these a cylindrical body. And the last set of figures is for a sphere. Again, if you read the corner, that it is written as it's a sphere. The center is 0, it is going out, and the radius is equal to r0. So we calculate the Fourier number, calculate the Biot number. So 1 by Biot number out here. Go to the left hand side, find out what is equal to your heat transfer coefficient. Sorry, what is the temperature that is there? Sorry, not heat transfer coefficient. What is the temperature at the center of the body? Next comes the temperature distribution at different locations in the sphere, just like we had seen before. And this is the heat transfer, rate of heat transfer in a sphere for unsteady state heat conduction. Once you know the Fourier number and Biot number, you can do all these calculations from the chart. Before I end, let me just do one problem trying to show you how to use these charts. So, and if you notice that a lot of these unsteady state heat transfer problems are actually practical situations, very practical situations that we face in everyday life. So let us look at this problem and see what it is. A rectangular slab of butter, which is 46.2 mm thick, at a temperature of 277.6 Kelvin in a cooler, is removed and placed outside where the temperature is 297.1 Kelvin. The sides and the bottom of the butter container can be considered to be insulated by the container side walls. the flat top of the butter is exposed to the environment. So what do we have? We have a slab of butter like this. We have a slab of butter like this and out here, okay? And you are told that this is the thickness of this butter slab, you are told, and you are told what is the temperature. This has been, now this butter has been taken out and kept on a table or something like that, and the sides and the bottom of the container can be considered to be insulated. So this is insulated, the bottoms are insulated, all the sides are insulated. So no heat is going out from here, no heat is going out from here. So the only heat that is escaping is from the surface, top surface, which is there. The top surface of the butter is exposed to the environment. The convective heat transfer is constant and is equal to 8.52 watt per meter square Kelvin. You're given the physical properties of butter. Calculate the temperature of the butter at the surface. But the surface, what is the temperature? At 25.4 millimeters below the surface. Let me just change my color, ink color. So we have to find out 25.4 millimeters from the top surface below the surface, and at 46.2 millimeters below the surface at the insulated bottom after 5 hours of exposure. This one and this one. And this is after 5 hours of exposure. Now let us see what we have. Since the heat is entering the slab of butter only at the top surface and the bottom is insulated, the slab can be considered equivalent to a half plate of thickness x1. Now if I go back and show you this picture, here, look at this. Now the bottom is insulated, only heat is going out from the top. So the butter can be considered to be half of this. So this is what we have. That means because the bottom is insulated, no heat is going out of the system. In this picture, heat was going out from the top surface and heat was also going out from the bottom surface, these two surfaces. But here we have been told that the bottom surface is insulated. The sides are also insulated. The only way the heat goes out is from the top surface. So that is why we are not considering this to be the entire slab. We are considering it to be only half the slab. So let us see this half the slab out here. So this is my half the slab. And so that means my thickness, that is x1, is equal to 46.2 millimeters. And for butter, the thermal diffusivity can be calculated. Thermal diffusivity, in the last problem, we were given the value of alpha. In this case, we are not given, but we can calculate it. What is thermal diffusivity? K by rho Cp. We have been given the density value, the Cp value, and the K value. So let us calculate it. So when we calculate, this is the value of K. This is what is your density. This is your Cp value converted into joule, not kilojoules. And this is my value of alpha, a very small factor of 8.58 into 10 to the power minus 8. M, the term M was equal to K by Hx1. So we find out what is the value of M. And we also find out the value of X. That is the Fourier number. That is alpha T by X1 squared. We know all the values, so this is equal to 0.72. So now let us see how we can do the estimation. Now if I go to this particular figure, my x-axis is my Fourier number. My Fourier number was the value of 0.72. So 0.72, we go up from here, straight up. And where do we meet? We have to now find out what is so the first problem is where we have to have the surface temperature. So when we have the surface temperature, I can look at this particular case out here. So in a surface temperature, we want to find out the temperature out here. So that means my x, which is going from the base to the top, my x is also equal to my x1 value. So x is equal to the full thickness, that is 0.0462. This divided by the x1, so my n value comes out to be equal to 1. And my m value was 0.5. So we look at these values. So m is equal to 0.5 out here. For this set of figures, this m is equal to 0.5. And here we find out under which condition is n equal to 1. The last line is the one where we have n equal to 1 and m equal to 0.5. So we extend this line till we reach the line which is going off from my Fourier number 0.72, and this is where it intersects. So from here we go to the left hand side and we find out what is the value. This value is equal to 0.25. So my y value is equal to 0.25, and knowing the definition of y, I can write this as, now my t is equal to minus 0.25 into 297.1 minus 277.6 plus 297.1, which gives me a value of 292.2 Kelvin at the surface of the butter. Now, the next problem was, on the next part was, that this was at the surface, and the second one was 25.4 millimeter below the surface. So 25.4 millimeter below the surface was in this direction. So 25.4 millimeter is out here. Okay. So since my x is going in the opposite direction to this, what we can do is that we can find out what is, so my x direction has to be equal to x1 minus this 25.4. So x1 minus 25.4, that is, this is my x1 value, minus 25.4 is this. This gives me the value of x. So this is my x value, this is my x1 value, and this gives me the new value of n. N is the distance at which I want to find out the temperature. So again, my Fourier number has not changed. It is still 0.72. So from this value of Fourier number, I go up again out here. And now what has changed is my m value has not also changed, but my n value has changed. So we have to go to the new line of n equal to 0.45 and find out what is the value of the y value, which is 0.44. We find out the value of 0.44 out here. And this gives me the temperature at the distance of 25.4 is 288.52 Kelvin. All right. And the last one is where we were asked to find out the temperature at 46.2 millimeter below the surface at the insulated bottom. So if I do that, let us see, because it is the center value that we want to find out, instead of using this particular figure to do my calculations, I will use the Hessler chart, which will give me more accurate answers. So for the Hessler charts, my x value is again 0.72, my m value is 0.5, and we can use this out here. So x value is 0.72, my m value is 0.5. We go up straight up here, find out what is the value of y naught, which is equal to 0.53. Put it in the expression, and you can get the temperature, which is there at the bottom of the slab, that is 286.77 Kelvin. So that finishes off what I wanted to tell you or teach you about this unsteady state heat transfer. So the first and the foremost thing that we had done in this was to understand that in the case of unsteady state heat transfer, there could be variations in temperature with respect to distance as well as with respect to time. So for the first model that we considered, which was the lump parameter model, in that case, the distance was not a factor because the temperature at any point in the solid was considered to be constant. This is possible only when we have a very high rate of heat transfer, high thermal conductivity inside the solid, or when the size of the solid is small. And we have found out how to find out how the temperature changes with time. The next case is when we cannot use a lump parameter model, and we have understood three types of cases out here. The first one was the case where we had there was no convective heat transfer resistance, only conductive heat transfer resistance inside the slab, which was there, and we found out how to calculate the temperature by using that infinite Fourier series. The next one was when we had tried to understand when we have a semi-infinite slab and how we can calculate the temperature at any position at any point of time. And the third case is when we considered a flat plate where it is the infinite long in the y and the z direction, but limited in the x direction. That is the difference between the second case and the third case. The second case, the x was infinite, In the third case, X is limited, but Y and Z is infinite. So in that case, how we can use this Hessler charts, etc., and other kinds of charts to find out the temperature at any distance and at any point of time. So this is where I will stop, and this is all I wanted to teach you in this course on heat transfer. We still can have some more classes in terms of our discussion hours, but as far as teaching is concerned, this is where I end. So I will stop sharing out here, and